In this video, we're going to do two example problems, one looking at inductors and one looking at capacitors, and just find the equivalent inductance or equivalent capacitors. Now, we really shouldn't look at these problems as being hard because we've already found equivalent resistance, and so we're really just using the same formulas. We're just having to apply them correctly on whether they're inductors or capacitors. Now, I did this kind of complicated circuit here. It's not really complicated, but with a lot of components, just to make sure we get practice on doing lots of the combinations. Now remember, the general rule of thumb here is to start on opposite side of LEQ. So I want to start on the other side here. So I'm going to look at these two, this kind of set of inductors here. Well, with this being diagonal here like this, I want to show you, they often draw them like this, but this sometimes confuses people, and there's another way to draw these here to make it, I think, less confusing. And I purposely drew it like this because a lot of texts will have a problem that looks like this, and people, get all concerned or confused about it. But I want to just remind you here that, for instance, this is a node here. So I can, and this node here, this is all one node, right? So I can move this point of the wire anywhere along this node. I don't have to have it connecting all the way over here in the corner. I can have it connecting anywhere. Similarly, this here is all one node. And I can have this point here connected anywhere on that. So what I'm going to do here, that's a 10 Henry, so I'm actually going to erase that inductor and simply draw it like this and put 10 Henrys in here. And by doing that, I think it becomes a little bit more obvious then that these two these two inductors are in series, and then I'm going to get a whole bunch of inductors in parallel. Now, what I'm going to be doing here, just so you're aware, I'm going to be kind of erasing parts of the diagram and redrawing them as opposed to constantly redrawing the circuit. If you don't feel comfortable doing that, of course, just redraw the circuit every time you've made a combination. But the first thing we can clearly see here is we're going to combine these two inductors, and we're going to combine them in series. So we would get 15 plus 25, which is 40 Henrys. So now what I'm going to do here is erase those. I'm not going to erase this bottom bridge. Well, I'll go ahead and erase it. And so I've got 40 Henrys now. So now I've got an inductor here that's equivalent inductance is 40 Henrys. And now what I can clearly see here, if I'm careful, is I can see that these two inductors are in parallel. Now the temptation is to say that all three of these are in parallel, and well, actually they are all in parallel. I was going to say the temptation here, I just have to make sure, because how do we know they're in parallel? Well, they're all attached to this top node, and they're all attached to this bottom node. So those three inductors are in parallel. So again, if we do the parallel combination, and I'm going to do, since it's 3, I'm going to do 1 over 12 plus 1 over 10 plus 1 over 40, and the reciprocal, which gives us 4.8 Henrys. So again, I'm going to kind of erase some things now. So I'm going to erase this stuff here, erase that a little bit, and instead of, I'll just draw this, instead of being 12, this is now 4.8 Henrys. Now we have the same kind of thing that's going on here. We have this little diagonal thing going on. You might say, well, wait a minute, how do I take care of that? If you want to draw it straight, we can draw it straight again, but we have to kind of slide things over here. So we're going to have to kind of slide things over. Now it's not necessary to do this, but I'll draw the picture here with these kind of slid over so that it's clear what configuration they are in. So I've got an inductor here, it goes down. That's terrible. For some reason, my hands never want to draw inductors very well. I don't know why, but I've never been able to draw inductors very well. All right, so let's label this again here. So this was 4 henries. This is 21 henries. This was 44 henries. And this is 1.2 Henry. And this is 4.8 Henry. Now, as I said, it's not necessary to do this, but what I did, again, is these diagonals sometimes confuse people. So what I did is I just moved this point and moved it over and basically just kind of stretched the wire out to make it vertical. But if I move this point over, well, this inductor has to kind of get pushed over as well. And then I'm also pushing this inductor over as well so that I can get a nice little wire here. So the easiest way to see that it's the same circuit is just look at your nodes. I've got a node here, and what's connected to it? The 21, the 4, the 44, and the 4.8. This node here, the 21, the 4, the 44, and the 4.8. Look at this node. What's connected to it? The 44 and the 1.2. 44 and 1.2. And then clearly this node right here has just got the 4.8 and 1.2. 4.8 and 1.2. So it's absolutely the same circuit. The node connections are identical. But for some people, it's much easier to see with this circuit right here the next step. And the next step, of course, would be here, I'll start it in red, is that we have these two components here that are now in series. And so we'd have 4.8 Henry plus 1.2 Henry, which of course just gets me 6 Henrys. And so I'm going to go ahead and erase some of this, because now what I basically have is a 6 Henry inductor. And then we can clearly see here, and actually there's a couple things, I'm going to do 2 of them here. We can clearly see that these 2 inductors are in parallel, and that these 2 inductors are in parallel. So let's go ahead and do both combinations of those in parallel. So we would have, well, I'll go ahead and do the 44 times 6 over 44 plus 6. And then this would be equal to, let me just punch it in my calculator real quickly. I get 5.28 Henrys. And then the other one, which is 4 Henry, so it'd be 4 times 21 over 4 plus 21, or I wrote it backwards here, which again, just punching that real quickly into my calculator, I get 3.36 Henrys. Now, again, if I kind of redraw my circuit just a tiny bit, I'll erase these here, because now this inductor is a 5.28 Henry inductor. And if I look here at the top of the circuit, this is not a 4 Henry inductor, this is a 3.36 Henry inductor. And now these are in series, and inductances in series add. So finally, I can get that LEQ is equal to 3.36 plus 5.28. And because I don't trust myself with arithmetic right now, I'm going to double check this computation on my calculator, and we get 8.64 Henrys as the equivalent inductance. Now, going back to the original circuit, this is not in reality a circuit you would ever build. The pure purpose of this circuit is just to get practice with combining inductors in series and parallel. There is no practical application of the circuit that I drew here. All right, but let's move on and do an example with capacitors. So let me scroll down here, and I've got another one already drawn. And again, you might want to pause the video to draw the circuit out in your notes. And I'm looking for the equivalent capacitance here. Now, just like I did before here, I'm going to redraw the circuit slightly because I've got a diagonal diagonal capacitor here. And so I'm going to kind of stretch that out so I can see a little bit clearer here. So let me first go ahead and erase some of this. And by dragging it out, I mean I'm going to have my circuit looking like this here, where this is 32 nanofarads, this is 8 nanofarads, and then this is 5.6 nanofarads. So all I did was redraw it so I don't have that diagonal there. And again, the only reason I do that is sometimes people find it easier to see series and parallel combinations. Now, the key thing here, and it's an easy mistake to make, and I make this all the time, is to make sure you use the correct formulas for capacitors, because remember, we're in the opposite case, where if they're in series, we use the parallel formulas, and if they're in parallel, we use the series formulas. So again, we start on the very opposite side, so what we should first look at is that we have these two capacitors here that are clearly in series. So, and being in series means that we would do the formula that we've usually used for parallel. So combine those in series, I'd have 32 nanofarads times 8 nanofarads over 32 nanofarads plus 8 nanofarads. Now, if you haven't already thought about this or done this, yeah, this example is in nanofarads, whereas the previous one was in henries. You don't have to be punching in this nanofarad in this case for all of these capacitors, and that's because every single capacitor is nanofarad. So I can essentially drop the nano for now and just combine them using numbers and just recognizing that the answers I'm always getting are in nanofarads. And on the next combination, I'll illustrate what I mean precisely with that. But let's go ahead and do what this combination here is. So I will quickly punch this into my calculator. And I wind up getting that this is 6.4 nanofarads. So again, let me redraw. I'm going to redraw this circuit. But now what I have here is a single capacitor. And this is 6.4 nanofarads. Now, I can clearly see that these two capacitors are now in parallel. So I've got these two that are in parallel now. So parallel combinations, remember we add the capacitance. So this would be in here, this is what I'm talking about. I'm dropping the nanofarad for now, and I'm just saying, well, that would be 5.6 plus 6.4, because they're both nanofarad. And then if I do that, I get that this would be equal to 12. And then I'll go ahead and tap back on that it's 12 nanofarads. And so what I'll do here is erase some of the circuit. And then this is now 12 nanofarads. Now I have, again, two capacitors in series. I'll circle what ones we have in series. And so I would combine them using my parallel formulas. And so I would, again, since it's just two, I always use the ones where you can just multiply. I mean, you could do the 1 over 18 plus 1 over 12. You could do that, but I just like using this formula. And again, I'll punch this into my calculator real quickly. And when I do that, I get 7.2 nanofarads. So I will erase this portion of the circuit now and realize that I have here now a 7.2 nanofarad capacitor. And now these two capacitors are clearly in parallel. Actually, we've been circling those in red, so let me continue that pattern. Those are in parallel. And so that would just be 12.8 plus 7.2, which is 20 nanofarads. So let me erase some of that. And so this is now 20 nanofarads. And now I'm left with 3 capacitors in series. Now since I have 3 capacitors in series, these 3 capacitors in series, what I'm going to do is I'll do the formula that CEQ is going to be equal to 1 over 8 plus 1 over 20 plus 1 over 40, the entire thing inverse. Now remember that everything's just automatically in nanofarads because that's the unit we started with. And when we do that computation, I wind up getting 5 nanofarads as the equivalent capacitance. So really, combining capacitors and inductors in series and parallel is not difficult. It's the same formulas we use for resistors. We just have to remember that capacitors kind of combined in an opposite way, where the capacitors in parallel, those capacitance is add. And then the ones in series use that parallel formula. The other thing I want to point out is, again, that the original circuit is not an actual legitimate circuit that has any use for any reason. It's just, again, something that we did to practice doing parallel and series combinations of capacitors. All right, so this is going to wrap up our kind of introduction to capacitors and inductors. The next lessons we're going to actually talk about, and this is actually the next lessons we'll finish up the course, is we're going to be talking about what happens when you have RL and RC circuits. And we'll also talk about some of the applications of those as well. We'll look at what the responses are, and you might say, well, what's the purpose of this? And then we'll give you an example on why these things are useful.